Today, I will be helping you to prepare for your forthcoming Exam 1. This question is about Lewis structure. So you've been asked to draw the Lewis structure for the compound that is showing on the screen. Now, to solve this problem, I'd like to explain this concept using bonding pattern. So let's determine the bonding pattern for carbon as well as other atoms in this molecule. So carbon has a valence electron of 4. So that means we have 1, 2, 3, 4. So each single electron would like to be paired up with some other electron. So this simply means that this carbon can form 4 bonds. So the bonding pattern of carbon is going to be this carbon with 4 bonds around it. Now the other atom here is oxygen. So oxygen has valence electron of 6. So you would have 1, 2, 3, 4, 5, 6. So that means a neutral oxygen atom can form 2 bonds and it will have 2 lone pairs. So sometimes oxygen can lose 1 electron. When oxygen loses 1 electron, we'll give it a positive charge. And that also means that that particular oxygen can form 3 bonds. So a positively charged oxygen atom will have 1 lone pair and 3 bonds around it. Also, oxygen can accept or gain an extra electron. So when it gains an extra electron, we will give it a negative charge. This means it has only 1 single electron. And this tells us that this particular oxygen can form just 1 bond. In other words, a negatively charged oxygen will have 3 lone pairs and 1 single bond. Since a hydrogen atom has just 1 electron in its valence shell, so it can only form 1 bond. Alright, so let's use the bonding pattern to form the Lewis structure of this compound. So we have 2 carbons. Two carbons, 5 hydrogens, and 1 oxygen. So here's what I'm going to do. So try to connect the carbon atoms this way. So since there's a positive charge in a molecule, I want to use this. So what you have to do is to try to connect the atoms. So at this point, we can begin to distribute the hydrogens. So we have 1, 2, 3, 4, 5. So we have 5 hydrogens. So we have dangling bonds, 1 on carbon and 1 on oxygen. So what we'll do is to connect those dangling bonds. Connecting them means you will have 2 bonds between carbon and oxygen. So before we can conclude, you need to also count the valence electrons on each of the non-hydrogen atoms to make sure that they obey the octet rule. So each atom should have 8 electrons in its valence shell. So for this central carbon, we'll have, and remember that 1 single bond contains 2 electrons. So you have 2, 4, 6, 8. That carbon has 8 electrons in its valence shell. So that satisfies the octet rule. This other carbon has 2, 4, 6, 8. That also satisfies the octet rule. For the oxygen, let me use a different ink here. The oxygen has 2, 4, 6, 8 electrons. So this means that this will be the correct Lewis structure for the compound. Let's go over another question. So here, we've been asked to draw the Lewis structure for this particular compound. The central atom here is carbon, and the neutral carbon will have 4 bonds. For nitrogen atom has 5 valence electrons. So that means we have 1, 2, 3, 4, 5. In other words, the neutral nitrogen atom can form 3 bonds and 1 lone pair. Now, sometimes nitrogen can lose 1 electron. If it loses 1 electron, then it will gain a positive charge. Then that means it can form 4 bonds. In other words, a positively charged nitrogen atom will have 4 bonds and no lone pair. And sometimes nitrogen can gain an electron. When it gains an electron, then we'll give it a negative charge. In that case, this nitrogen can form 2 bonds. So, a negatively charged nitrogen atom will have 2 bonds and 2 lone pairs. As for oxygen, so a neutral oxygen atom will have 2 bonds and 2 lone pairs. And we also know that for oxygen to have a positive charge, it will have 3 bonds and 1 lone pair. And a negatively charged oxygen will have 1 bond and 3 lone pairs. So based on this, let's try to draw the Lewis structure for nitromethane. So what I would do, we have 1 carbon, and I can connect the carbon with nitrogen. So this is our central atom here. Those 3 hydrogens belong to the carbon, and the 2 oxygen atoms belongs to the nitrogen. So they'll get attached to the nitrogen. So hydrogen, 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 they belong to the carbon. Let's start with this. Let's connect this nitrogen to this carbon. So you will have this. So I can connect 1 oxygen to this nitrogen and another oxygen to this nitrogen. However, this wouldn't make any sense. A single bonded oxygen should have negative charge. Negative, negative. However, in a compound here, the molecule is neutral. So this will be an incorrect Lewis structure. So we have to try a different connection or a different approach. So another thing I can do is to use this nitrogen. So connect that positively charged nitrogen with the carbon. So the other things I can do would be to connect this oxygen to this nitrogen. Notice there is a dangling bond. We have 2 dangling bonds here, 1 on nitrogen and 1 on oxygen. So we can connect those 2. And that will give you a double bond between the oxygen and nitrogen. Then I can bring one of these oxygen atom here. So I can connect this oxygen to the nitrogen. Notice that since in a molecule here, the net charge is 0, So here also we have positive and negative charge. So both positive and negative charges in that same molecule will cancel out. So the net charge is going to be 0. If you were to calculate the valence electrons in each of the non-hydrogen atoms, starting with carbon, carbon will have 2, 4, 6, 8 electrons. Nitrogen will have 2, 4, 6, 8 electrons. That oxygen will have, this particular oxygen will have 2, 4, 6, 8 electrons. And the other oxygen will have 2, 4, 6, 8 electrons. So the octet rule is satisfied in all of the atoms in this compound. Therefore, this will be the correct Lewis structure for nitromethane. So the next question here asks us to determine the hybridization of the various atoms. So A, we have nitrogen, B, oxygen, C, carbon, and D, bromine. So let's start with nitrogen. To determine the hybridization of that nitrogen atom, we have to use a formula that says steric number equals to number of atoms attached to the nitrogen plus number of lone pairs. So some textbook will write steric number, some other textbook will write VSEPR number. So for the nitrogen atoms, the number of atoms attached to the nitrogen is just 1, is carbon. And that nitrogen has 1 lone pair. So we're going to have 1 plus 1, which is equal to 2. If the steric number is 2, we're going to have sp hybridized orbital. So the hybridization of that particular nitrogen atom is sp. So let's determine the hybridization of oxygen. So we'll start by calculating the steric number for oxygen, which is equal to number of atoms attached. That oxygen has just 1 carbon atom attached to it. So we're going to have 1 plus number of lone pairs. The oxygen has 2 lone pairs. So you're going to have 1 plus 2, which is equal to 3. If the VSEPR number is 3, then you're going to have sp2. Therefore, the hybridization of the oxygen atom is going to be sp2. So the next one is carbon, C. That carbon has 2 hydrogens. Remember, a neutral carbon should have 4 bonds. So since it has 2 bonds to the other carbons, then that means the number of hydrogen it will have will be 2. All right, so the steric number in this case is going to be number of atoms attached to that central carbon atom plus number of lone pairs. So the atoms attached are 1, 2, 3, and another carbon, 4. So we have 4 plus, it doesn't have any lone pair, so we have 0, which is equal to 4. So if that's the case, the hybridization is going to be, of the 4 regions of electrodensity, S gets 1, the remaining 3 goes to P. So you're going to have sp3 hybridization. And the last one there is bromine. For the bromine, the steric number will be number of atoms attached plus number of lone pairs. So that bromine has 3 lone pairs, 1, 2, 3, plus how many atoms are attached to that bromine? Just 1. Okay, 1 carbon. So you're going to have 3 plus 1, which is equal to 4. Of the 4, S always gets 1, and then the remaining 3 goes to P. So you're going to have sp3 hybridization for that particular bromine. The next question says, which orbitals form this carbon-nitrogen triple bond? Carbon-nitrogen triple bond. So this is the carbon-nitrogen triple bond here. Now it wants us to determine which orbitals form the sigma bond between those two atoms. Now sigma bonds are formed by hybridized orbitals. And the way to determine the hybridized orbitals will be to use steric number. First of all, calculate the steric number and determine the hybridization. So whatever hybridization those atoms have, those will be the hybridized orbitals that we use to form this sigma bond. So we already know the hybridized orbital for the nitrogen. We determine that to be, that nitrogen has sp hybridized orbital. So we're going to determine the hybridized orbital for this carbon. So the VSEPR number is going to be number of atoms attached, which is 1 and 2. So the steric number for that carbon is going to be 2 plus 0. It doesn't have any lone pair, so it will be 0. So it's going to be 2 plus 0, which is 2, which gives us sp hybridized orbital. So this simply means that the nitrogen will use its sp hybridized orbital to form the bond with the sp hybridized orbital of carbon. So each atoms, the nitrogen and carbon, both use their respective sp hybridized orbitals to form the sigma bond. Now the next question asks us to determine which orbitals form the carbon-nitrogen pi bonds. Pi bonds are formed by p orbitals. So all we have to say here is that nitrogen uses p orbital to form a bond to form the pi bond with p orbital of carbon. Or we can just write this simply as p. So p orbital from nitrogen overlaps with the p orbitals of carbon to form the pi bond. But in the case of the cyano group, we have 2 pi bonds. Okay, so each of those 2 pi bonds are formed by p orbitals. So this question is on resonance. So here we've been asked to draw the resonance structure for the molecule showing currently. It's always good to be able to use your skill of curved arrow pushing to determine resonance structures. And whenever you want to draw curved arrows, you always draw curved arrows from electron source to electron sink. Electron sources usually will have excess electron density around the atom. Okay, examples of electron sources are lone pairs and bonds, such as pi bonds or double bond, triple bond, single bond. So that oxygen atom has 3 lone pairs. Now, one way you can tell that there is excess electron density is a negative charge. So negative charge is an indication of an excess electron density. And how do you know which direction to draw your curved arrow? If there is a positive charge, it simply means that that nitrogen atom lacks electron. So since that atom is deficient of electron, it needs electron. That means electron will go towards that direction. So you always draw your curved arrows from electron source to electron sink. So to draw this curved arrow, this lone pair, we're going to draw it from the lone pair on the oxygen. That lone pair is going to form a bond. In order not to break octet rule, we will have to break this bond, this pi bond, and the excess electron will go towards the nitrogen. So that pi bond will become the lone pair on the nitrogen. Now the resulting structure from that will be such that there is now double bond between the carbon and oxygen. Since oxygen has used one of its lone pairs to form the pi bond, it will now have 2 lone pairs on it. And because the oxygen donates electron, we're going to give that oxygen a positive charge. positive and negative charge on the same atom will cancel out, such that this oxygen would then be a neutral atom. Now, the pi bond between carbon and nitrogen is going to become a single bond. So we're going to assign negative charge to whichever atom that receives or accepts electron. So negative and positive charge on the same atom will cancel out, so that nitrogen will now have a neutral charge. And since the nitrogen gains electron, it will have a lone pair. This question asks us, 1, are these structures, are they resonance structures? To answer this question, you need to write out the characteristics of resonance structures. So resonance structures must have, for two compounds or structures to be considered resonance structures, they must have the same molecular formula, same connectivity, and same overall charge. So in terms of molecular formula, for the compound on the left, we have 3 carbons. 1, 2, 3. Oh, actually 4 carbons. So there are 4 carbons. So C4. How many hydrogens do we have? We have 3, 6, 7. 7 hydrogens. So C4H7. And we have 1 oxygen atom and a negative charge. So for the structure to the right, we also have 1, 2, 3, 4. We have 4 carbons. As for hydrogen, we have 3, making 6, then 7. So there are also 7 hydrogens in the structure. And we have 1 oxygen atom and a negative charge. So in terms of molecular formula, both structures have the same molecular formula. So all of these characteristics must be checked before we can confirm or state that these two structures are resonance structures. So next is connectivity. Do they have the same connectivity? Let's see. The methyl group here is connected to this carbon, which is connected to this oxygen. Here, this methyl group is connected to this carbon, which is connected to this oxygen. Now, that's carbon or carbonyl carbon is connected to a carbon with a hydrogen. Here also, that carbon, this carbon is connected to this other carbon with a hydrogen. And this carbon with a hydrogen is connected to a methyl group. Here, this carbon with a hydrogen is connected to a methyl group. Therefore, we will say that in terms of connectivity, they are both the same. Next is charge. Do they have the same overall charge? On the left-hand side, we have a negative charge. On the right-hand side, we also have a negative charge. So we're going to check all of these boxes. Since all of these boxes are checked, we can say that, yes, these two structures are resonance structures. So this question asks us to determine which of these is the major resonance structure. In order to answer this question, you need to look at the characteristics of a major resonance structure. What are the things that makes a resonance structure the major resonance form? 1, whichever structure has more atoms with full valence shell will be considered the major resonance structure. And you must follow these rules in this order. Now, if this doesn't help, the second rule, you then go to the second rule, which says that if there are positive and negative charges, whichever structure has the positive and negative charges close to each other will be the major resonance form. And if that doesn't help, then we go to the third rule, which says that whichever structure has negative charge on the more electronegative atom is going to be the major resonance structure, or positive charge on the less electronegative atom. So let's apply these rules to the structures above. So rule number 1, we have to start with rule number 1. full valence shell. All of the carbon atoms and all of the atoms here, or all of the non-hydrogen atoms, have full valence shell. For example, this carbon has 2, 4, 6, 8 electrons in its valence shell. This carbon has 3 bonds with the hydrogen, making 6, plus this bond to the carbon, making 8. So that carbon also has a full valence shell. The oxygen has 2, 4, 6, 8. So that has complete octet. This carbon has 1 bond to the hydrogen, which is 2 electrons. So that's 2, 4, 6, 8 valence electrons. The other carbon also has 8 valence electrons. 3 bonds with the hydrogen make 6 electrons, plus this bond here, making 8. So all the atoms here have full valence shell. For the structure to the right, this carbon has 8 valence electrons, 2, 4, 6, 8. This carbon here has 8 also. 6 bonds, 6 electrons from the 3 bonds to the hydrogen, and this bond making 8. The oxygen has 2, 4, 6, 8 valence electrons. The other carbon has 2, 4, 6, plus the bond to the hydrogen, making 8. This one has 3 bonds to the hydrogen, making 6 electrons, plus these electrons here, making 8. So all the atoms in both molecules or in both structures have full valence shell. So rule number 1 doesn't help us. Now we have to go to rule number 2. Rule number 2 says that there have to be 2 charges, positive and negative, and whichever structure have the charges closer together or closest together will be the major resonance structure. However, we have only 1 charge in each of them, so rule number 2 doesn't help us either. We then have to go to rule number 3. So this rule says that whichever structure has the negative charge on the more electronegative atom will be the major resonance structure. So in this structure here, this negative charge is on carbon. So this negative charge is on carbon. The negative charge here is on oxygen. Oxygen is more electronegative than carbon. Therefore, this is going to be the major resonance structure. The next question is on IUPAC naming. So we've been asked to name this particular compound. Now, to name this compound, the first thing you want to do is to determine the main chain. Main chain. And this is based on the number of carbons. So here we have 1, 2, 3, 4, 5, 6, 7. Since there are 7 carbons and that's the longest, the name of this main chain is going to be heptane. Next is to number the main chain. As a linear compound, we can either start numbering from the left-hand side or from the right-hand side. But how do we decide which end to start numbering from? We need to look at the substituent. Whichever substituent gives us the lowest numbering possible will be the end where we get to start numbering from. So consider this 1, 2. The first substituent is on carbon 2. For this other one, if you start from this end, the first substituent is on carbon 2. Now there is a tie. If there is a tie, what do? We go to the next atoms, or next substituents rather. So from the right-hand side, the next substituent is chlorine and is on carbon 3. How about if we were to number from the left-hand side? The next substituent is on carbon 4, which is the bromo group. Since chlorine, the chloro group will give us the lowest numbering, therefore we have to start numbering from the right-hand side. So this is how you decide which end to start numbering from. 1, 2, 3, 4, 5, 6, 7. The next thing would then be to list the substituents. So we have methyl group on carbon 2 and carbon 6. Let's list the substituents. So you would have 2-methyl. Between number and letter, you use a dash. We also have 6-methyl. Then we have chlorine on carbon 3, so we have 3-chloro. And we have bromine on carbon 4, which gives us 4-bromo. Next will be to group substituents that are the same. So if you have multiple substituents, you group them together. So in this case, we have 2 methyl groups. Since there are 2 of those, we will have di. The prefix we will use is going to be di. Now this becomes 2,6-dimethyl. The next thing would then be to name the main chain, name the compound. So to name the compound, you would name the substituent first, followed by the main chain. And in naming the substituent, you have to name them in alphabetical order. Alphabetically, B comes before C, which then comes before M. And whenever you're comparing or trying to determine which one to name, which substituent to name first based on alphabetical order, you don't compare the prefix. Okay, you only compare the first letter of the substituent. So in this case, it's going to be M and not D. So the first one is going to be this. Bromine comes first, followed by chlorine. C comes second. Then M comes third. So let's name this compound. We're going to start with 4-bromo. C comes second, so you have 3-chloro. M comes next, so you have 2,6-dimethyl. Then, now that we've finished naming the substituent, you can now go ahead and include the main chain. Heptane. So the name of this compound is going to be 4-bromo, 3-chloro, 2,6-dimethyl heptane. So we've been asked to name this compound. Again, we're going to follow similar pattern as above. The only difference is that the main chain here is going to be the ring. So let's identify the main chain or parent chain. So the parent chain is going to be the ring based on the number of carbons that we have in this ring. So this is 1, 2, 3, 4, 5, 6. So the name of the main chain is going to be cyclo because it's a cyclic compound. So cyclohexane. Hexane because it has 6 carbons. There are 6 carbons in the ring. So the next thing would then be to number the main chain. You have to number it in such a way that you will get the lowest numbering possible. And to get the lowest numbering possible, we will start from here. So wherever on the ring, wherever you have 2 substituents, usually you should start numbering from there because that will give you the lowest numbering possible, usually. So there are also the other way, either we can number clockwise or counterclockwise. If you number clockwise, the first substituent is going to be on carbon 3. If you number counterclockwise, the first substituent is going to be on 2, 3, 4. It's going to be on carbon 4. Again, we want to achieve the lowest numbering possible. So 3 is lower than 4. Therefore, we will number in a clockwise fashion. So 1, 2, 3, 4. I don't have to go all the way to 6. I can just stop here. So now that we've numbered the main chain, the next step would then be to list the substituents. So we have metal, metal, another metal. So we have metal group on carbon 1, another metal on carbon 1. So we have one metal. We have another one metal. We have another metal group on carbon 4. So that will be 4 metal. Then we have another substituent. Substituents are anything that is attached to the main chain. So if you look at this particular substituent, it has 3 carbons. So 3 carbons as a substituent will be propyl group, propyl. And since that propyl group is on carbon 3 of the main chain, on the main chain, it will be 3 propyl. Now, if there are substituents that are the same, we have to group them together. So we have 3 metal group. So we have to group these together. And since there are 3, the prefix is going to be tri. So we would have 1, 1, 4, trimethyl. So the next thing would then be to name this molecule. Name the compound. In naming the compound, you have to start with the substituent, again in alphabetical order, followed by the main chain. So we have P and M. M comes before P, so we're going to name this first, followed by the propyl group. Again, when deciding which substituent to name first, we don't consider the prefix. No, we only consider the first letter of that particular substituent, which is M. So to name this compound, this will be 1, 1, 4 trimethyl 3 propyl cyclohexane. Again, between letter and number, you use dash or hyphen. And between 2 numbers, you use comma. All right, so that would be the name of the compound. Next question. This question asks us to determine the geometry around the bolded atoms. So let's do that. Let's determine the geometry around this nitrogen in this compound. Let's start with this. What's going to be the geometry of the nitrogen atom? To determine the geometry, we must first determine the hybridization. And we know that SP hybridization will give you linear geometry. SP2 hybridization gives trigonal planar geometry. And SP3 is tetrahedral geometry. Tetrahedral geometry. So in order to determine the the geometry. Again, we have to start with the hybridization. And hybridization, you can use, you first of all need to determine the steric number or VSEPR number. VSEPR number or steric number. So this is the acronym for valence shell electron pair repulsion. So VSEPR number is, or steric number, is the number of atoms attached plus number of lone pair. We have 2 atoms attached to that nitrogen. 1, 2. So we have 2 atoms plus number of lone pair. We have 1 lone pair on the nitrogen, which is 3. So if the VSEPR number is 3 or steric number is 3, that means the hybridization is going to be sp2. S gets 1, there will be only 2 left for the p orbital. And if it's sp2, then the geometry is trigonal planar. Trigonal planar geometry. So that will be the geometry of the geometry around the nitrogen atom. The next question, we're asked to determine the geometry of this oxygen. Again, to do that, VSEPR number will be number of atoms attached plus number of lone pair. So on that oxygen atom, we have 3 hydrogens, or 3 hydrogen atoms, and 1 lone pair. So the VSEPR number will be 3 plus 1, which is 4. If there are 4 VSEPR number or steric number, the hybridization will be such that S gets 1, and the remaining, there will be 3 left for the p orbital. So you have sp3 hybridized orbital or hybridization. sp3 hybridization have a geometry of tetrahedra. So we can say that that particular oxygen atom will have a tetrahedral geometry. The next one was the geometry around that particular carbon in methane. Again, VSEPR number equals number of atoms attached. In this case, we have 4 atoms attached to the carbon. So that will be 4 plus 0, which is 4. 0 means there is 0 lone pair. So if the VSEPR number is 4, therefore the geometry is going to be, the hybridization will be sp3, and as such, the geometry will be tetrahedral. So that carbon atom has a tetrahedral geometry. So this question asks us to determine which of the compound below will have the highest boiling point as well as the lowest boiling point. To answer this question, you need to determine the type of attractive forces or attractive interaction that exist in the respective molecules. So for acetone, that has a dipole moment. So what that means is that oxygen is more electronegative than carbon. So this will be partial negative and partial positive. So the partial negatively charged oxygen could be attracted to the partial positive charge of the carbonyl group in another acetone molecule. So that attractive force is known as dipole-dipole interaction. That's the kind of attractive interaction that exists in acetone molecule. In acetic acid, since we have a hydrogen that is connected to the most electronegative atom in the molecule, this compound could do hydrogen bonding interaction. What this means is that in a molecule of acetone, of acetic acid, Okay, so of course, the hydrogen is partially positively charged because the oxygen pulls electrons away from the bond connecting itself and the hydrogen. So the hydrogen is partially positively charged and oxygen is partially negative charged. So what does it, what simply mean, what this means is that this proton could hydrogen bond to this oxygen, to the carbonyl oxygen, and this oxygen could form a hydrogen bonding with this proton in another molecule of acetone, of acetic acid. So this is hydrogen bonding interaction. And hydrogen bonding interaction is a stronger attractive interaction than dipole moment. So based on this, we will say that acetic acid will have the highest boiling point for the 2,2-dimethyl propane or neopentane. Both that and the pentane they both have dispersion interactions. They both can do dispersion interactions. Also known as London forces or van der Waals forces. Now, the more branches you have, the less surface area of contact and less dispersion interaction you would have. For example, if you have two molecules of this, the branch will prevent it will limit the surface area of contact. Whereas for pentane, there is the possibility of, because it's linear and it has no branch, there is you could have high or large dispersion interaction due to more surface area being in contact. So because of this reason, the 2,2-dimethyl propane will have the lowest boiling point. Lowest boiling point. Acetic acid will have the highest boiling point. This question asks us to identify the most stable and the least stable conformations. So these are different conformations of a substituted, tri-substituted cyclohexane. Now, whenever you have bulky groups in axial positions or axial bonds, they destabilize the compound, the conformation the more. So in the first molecule, there are 3 ethyl groups in axial position. So here we have 3. Here we have just 1. Here we have none. Here we have 2. So since the first one has more ethyl group in the axial position or on the axial bond, that particular conformation would experience the highest form of destabilization. So we'll have more destabilizing interaction there. Therefore, this will be the most unstable, which is also the least stable. So the least stable is going to be the first molecule. Least stable, due to it having more ethyl group or bulky group in axial position. And the most stable is the molecule where there is no ethyl group, no bulky group in axial position. So this will be the most stable. In other words, for the conformation to be more stable, it needs to have more bulky groups in equatorial position. So based on that, we'll say that this has all of its ethyl groups or bulky groups in equatorial position. Therefore, it will be the most stable. whereas this one has no bulky group or no ethyl group in equatorial position. So it will be the least stable. So this question is about functional group identification. We've been asked to identify all the functional groups in this molecule. So when you have hydroxy group being connected to a carbon, that's an alcohol. And the type of alcohol we have here is secondary alcohol, and that's because the carbon that has the OH group is attached to two other carbon atoms. Therefore, we'll say this is secondary alcohol. Another group here is where you have the OH group attached to a benzene ring, and we call that phenol. Another one is alkyl halide. Alkyl halide. Bromine is a halogen. So when you have a halogen that is attached to a carbon, to an alkane, we call it alkyl halide. And the type of alkyl halide we have here is tertiary alkyl halide. And that's because the carbon that the bromine is attached to is connected to three other carbons. 1, 2, 3. Therefore, we call this tertiary alkyl halide. This is alcohol here. Now, another functional group is aldehyde. Aldehyde is when you have a carbonyl group that is attached to, so carbonyl group is carbon that's connected to oxygen via double bond. And that carbonyl carbon is attached to a hydrogen and a carbon. So we call this aldehyde. The next functional group I see here is amine. Amine is where you have nitrogen atom that is attached to maybe 3 carbons or carbons and hydrogens. Okay. So the type of amine we have here is secondary amine, and that's because the nitrogen is attached to 2 carbon atoms. So we call this secondary amine. Another functional group here is amide. Amide is when you have a carbonyl group that is attached to nitrogen. That's an amide. So these are all of the functional groups in this molecule. And this is how you can identify the different functional groups in a molecule. So this question asks us to determine the most stable conformation as well as the least stable conformation using templates given. So the template given, we have template A and template B. Now to solve this question, it's always a good practice to draw out the Newman projection by yourself. And to draw the Newman projection, if you view this compound from this angle that we have here, view this compound from this angle, remember that wedge bond simply means that that bond is coming out of the screen and pointing towards you, okay? Whereas right now, this hydrogen that is on a dash bond is pointing away from you towards the back of the screen. So if you stand on this side, on the left-hand side, and view that carbon through this bond, we will represent the front carbon with a dot. Now, both of these groups are above your eye level. That means they're pointing upwards, whereas the methyl group extends downward because it's below your eye level. Of these two groups that are pointing upwards, the third butyl group is on a wedge bond. So standing here and viewing that carbon, that wedge bond is going to be to your right-hand side. So third butyl will be drawn upright. The hydrogen is on a dash bond, is going to be towards your left-hand side when viewed from that angle. The methyl group will extend downward. So that's how you're going to distribute those substituents on the front carbon. Next, we will have the back carbon. So we're going to represent that back carbon with a big circle, and I'm talking of this carbon. So the hydrogen is on a wedge bond. So that means that hydrogen will be pointing to your right-hand side, be on your right-hand side. The isopropyl group will be to your left-hand side. Hydrogen will be to your right, the isopropyl will be to your left, and this methyl group will be pointing upward because it's above your eye level. So the methyl group, you draw it upward. The hydrogen will be to your right and it's pointing downward. And the isopropyl group will be to your left. So that will be the Newman projection for this compound. But remember also that the compound, the question says you should draw the most stable conformation. The most stable conformation will be the conformation in a staggered conformation. It's going to be one of the staggered conformation. And it's usually the conformation where the two biggest groups are anti or opposite each other. So the biggest group on the front carbon is the third butyl group. The biggest group on the back carbon is the isopropyl group. Now those groups are anti or opposite each other. Then we have the other bigger group too. The methyl groups on both carbons are also anti each other. So we'll call this conformation anti-staggered conformation. Anti-staggered conformation. And that will be the most stable conformation. So the next thing would then be to find a way to transfer the substituents on the templates that were given. So if you look at the template, this is the front carbon, the bond on the front carbon. So here's my front carbon here. Here are the bonds on the front carbon. So what I'm going to do is to find a way to orient this Newman projection such that it aligns with the template. Then it will be easier to transfer those substituents on the template. So now I know that the third butyl group will be here. The hydrogen will be here. This methyl group then will be here. So that's for the front carbon. As for the substituent on the back carbon, I have this methyl group, which I will write here. I'll place the methyl group there. Then I have this hydrogen, which I will place here. Then I have this isopropyl group, which correspond to this bond, isopropyl. So that will be the most stable conformation. The next would then be to draw the least stable conformation. So the least stable conformation will be when you have the biggest groups on the front and back carbon very close together in an eclipsed position, in an eclipsed conformation. So I want to rotate this molecule in such a way that the two biggest groups will be close to each other. So what I will do will be to keep the front carbon and rotate just the back carbon. So if I rotate the back carbon, then that means that this isopropyl group will go 60 degrees, another 60 degrees, another 60 degrees. So I have to rotate that back carbon by 180 degrees in order to achieve my desired goal. So the third butyl group is here. I'm drawing out the front carbon. The substituents on the front carbon. Hydrogen is here, and I have methyl group. So those are the substituents on the front carbon. So if I rotate the back carbon by 180 degrees, now that isopropyl group will be next to that butyl group. So I'm going to have my isopropyl group here. Then that means every other substituent on the back carbon should be rotated by 180 degrees. So that means this methyl group that's on the back carbon will be rotated by 180 degrees, 60, 60, 60. So that methyl group is going to be right next to this methyl group in the front carbon. Then the other substituent on the back carbon is this hydrogen. So if I rotate that hydrogen by another 180 degrees, so that's 60, 60, 60, then it's going to be right next to this hydrogen here. So that means that hydrogen on the back carbon is going to be there. Now this conformation, which is an eclipse conformation, will give me the most unstable or the least stable conformation. So least stable conformation or least stable Newman projection, and this will be the most stable. All right, let's go over to the next question. So this is about cyclohexane chair conformation. So the question wants us or asks us to draw the chair conformation for the substituted cyclohexane. So draw the chair conformation, then draw the ring flip, and then determine which chair conformation is more stable between the ring flip and the chair conformation. All right, to draw a chair conformation, first of all, you have to start by drawing two parallel lines. Then start drawing a line from these two ends. Draw a line towards each other and stop midway. Then connect this point to this point and then connect this one here. So you have your chair conformation. Next will be to number the carbon, the ring. Usually it's a good practice to start numbering from here or from here. It makes life easier for you. So let's say this is my number 1 and this is number 2, number 3, number 4. The goal is to be consistent in your numbering. So if you number through clockwise, then you should go clockwise also in the chair that you just draw. So if this is 1, then this should be 2, 3, and 4. So the next thing would then be to assign the substituent. Before assigning the substituent, it's worth noting that we have to assume that wedge means up and dash bond means down. So since carbon, the bromo group on carbon 1 is on a wedge bond, so let's draw out the different bonds on the numbered carbon atoms. So carbon 1, the axial bond usually will point vertically up or vertically down, depending on the direction of the carbon. So if the carbon is pointing up, the axial bond points up. If the carbon is pointing down, like carbon 2 is pointing down, the axial bond on that carbon will point downwards. We also have another substituent on carbon 4. So the axial bond on carbon 4, since that carbon 4 is pointing down, the axial bond will point downwards. We can now go ahead and draw the equatorial bonds. Equatorial bonds usually point sideways. It could be sideways, up or down, depending on which direction the axial bond on that carbon is pointing. So if the axial bond on the carbon is pointing up, the equatorial bond will point horizontally down. If the axial bond is pointing down, the equatorial bond will point up. And if the axial bond is pointing down, the equatorial bond will point upward. When drawing the equatorial bond, try to make it align with for example, when I draw this, I will try to make sure this is in alignment with this. Like it should be parallel to it. And when I want to draw this equatorial bond, I want to make sure that it's parallel to this. And when I want to draw this equatorial bond, I want to make sure it's parallel to this. So that's the idea. All right. So this is up, this is down, up, down, up, down. So the bromo group on carbon 1 is pointing upward because wedge means up. So the up on carbon 1 here is going to be this. So this is where I'll draw the bromo group. Okay, automatically hydrogen will be on this bond. Because hydrogen is implied, is implicit in the carbons. So wherever we don't usually show hydrogens on carbon. So if you have the bromo group on a wedge bond, so that means there's a hydrogen on the same carbon that's on the dash bond. That means there's a hydrogen on this carbon that's on the dash bond. On carbon 2, the bromo group is on a wedge, meaning it's up. So that means I want to place that bromo group here. Automatically, the hydrogen would point down to be here. Since this bromo group here is on a dash bond, dash means down. So that means that bromo group has to be here. And hydrogen will be up. So this is how you should distribute the bonds, the substituents on the cyclohexane. But usually we don't show hydrogen on carbons. So I might as well just erase all of these hydrogens to make my cyclohexane look a little bit neat. The question also said then draw the ring flip or chair flip. So to draw the chair flip, I will also start by drawing two parallel lines, but in opposite direction to the chair conformation on the left-hand side. Again, start drawing lines from these ends and stop midway. Connect this to this and this to this. And so you have your chair conformation. So when you flip the chair, this carbon that is here that was pointing up, carbon 1, will now point downward. Carbon 4 that was pointing down here will now point upward. So all of the carbons will flip. So this is carbon 2. This is carbon 3. Carbon 3 is up here. Here it's going to be down. So that's the idea behind chair flip. Again, recall that we number sideways, we number clockwise, so you should also maintain be consistent. Also make that numbering to be clockwise. Next, we can now go ahead and assign the substituents. But before doing that, I would like to draw the bonds on each of the carbons. So carbon 1, since that carbon is facing down, the axial bond will face downward. On carbon 2, the carbon 2 is facing up, so the axial bond will face upward. On carbon 4 is facing up, the axial bond will face up. Just draw it vertically up. You can now go ahead and draw the equatorial bonds. Equatorial bonds will always be horizontal, but it could be horizontal up or down. It has to be opposite the axial bond. So since on carbon 1, the axial bond is pointing down, equatorial bond will point upward. The axial bond is pointing, on carbon 2 is pointing up, equatorial bond will point downward. But you want to make sure that that equatorial bond will be parallel to these lines. Okay. So to draw that equatorial bond, you should go this way. The equatorial bond on carbon 4, since that axial bond is pointing up, equatorial bond will point downward. So since these lines, and it has to be parallel to this line, so again, bromine is on the wedge bond on carbon 1, it's up. Up should remain up in all cases. So bromo group is up, so the bromine will be here. Automatically hydrogen will be here. The bromo group here is up on carbon 2. Therefore, hydrogen will be here. The bromo group on carbon 4 is on a dash bond. Dash is down, so I'll place the bromo group down. Hydrogen will be here. I don't need to show the hydrogens on carbon, so I'll just go ahead and erase these hydrogens. So this will be the chair flip or ring flip. The next question then asks us to determine which of the chair conformation is more stable. The more stable will be the one that have the bromo group, which is the bulky group, in the most equatorial position. So equatorial bromo group here is just 1. The equatorial. So the bromo groups on equatorial position here is 1, 2. The more bigger groups or bulky groups that are in equatorial position, the more stable the molecule will be. So therefore, the more stable conformation is going to be this. So this will be the most stable conformation. You can also do this in terms of axial bonds. The more bigger groups that are on axial position or axial bond, the more destabilizing the conformation will be, and the more unstable it will be. So since this chair on the left has 2 bulky groups or bromo groups in axial position compared to the one here, therefore this chair conformation will experience the more destabilizing interaction. Therefore, it will be the least stable conformation. So this question asks us to determine the strongest base as well as the weakest base. Since all of these compounds are negatively charged, so the first thing you want to do is to determine the conjugate acid of each of those bases. And conjugate acid is what you get when you add a proton to each of the bases. So add a proton to each of them. That will give you the conjugate acids. So when you attach a proton to this compound, to this base here, you have alcohol. The acid is going to be alcohol. When you add a proton to this base, then you will have NH2. So whenever you add a proton, you will assign a positive charge. So positive charge on this oxygen will cancel out, so you have a neutral molecule. Positive charge on this negative charge on the same atom, on the negative, a positive charge on the same nitrogen atom where there is already a negative charge. The charges will cancel out, you will have a neutral amine. If you add a proton here, you would have this. Of course, if you have to assign a positive charge to the same carbon atom, which will cancel out the negative charge. So you have a neutral cycloalkane. Here, the conjugate acid will be carboxylic acid. Give this oxygen a positive charge, and you have a neutral carboxylic acid. So you have alcohol, you have amine, you have cycloalkane, you have carboxylic acid, carboxylic acid. More specifically, you have acetic acid here. Then go ahead and assign the pKa, and whichever pKa is the highest, would be the strongest base. And whichever pKa is the lowest will be the weakest base. So the alcohol have pKa of 16. Amine has pKa of around 38. Alkanes have a pKa of above 50. Carboxylic acid has a pKa of 4.75 or 5 approximately. So of all of these conjugate acids, the one with the highest pKa is alkane or cyclohexane with pKa of over 50. So that means this compound will be our strongest base. The weakest base will be the one with the lowest pKa. So since this is the lowest pKa, and this conjugate acid has the lowest pKa, so this will be our weakest base. Let's go to the next question. So this question is asking why acetic acid is a stronger acid than ethanol. If you want to check whether an acid is strong or how strong or weak an acid is, first of all, determine their conjugate bases. So this is going to be the opposite of what we did in question 11. So if these are the acid, the conjugate base is whatever that is formed whenever you pull off a proton. So what you have to do here is to remove a proton from each of these acids. So removing a proton from here will give you this conjugate base. And removing a proton from this will give you this conjugate base. So the question now is, which of these conjugate base is more stable? Whichever conjugate base is more stable will give you the stronger acid, because the acid wants to lose its proton rapidly to form a more stable conjugate base. But any acid that forms a weaker conjugate base, a less stable conjugate base, therefore doesn't want to form that less stable conjugate base, because naturally compounds wants to form something that is more stable. Now, since we have negative charges on oxygens, the acidity trend we're going to use here is resonance. One of them can do resonance, the other cannot. For example, this conjugate base can do resonance. So that means the negative charge on this oxygen can be stabilized by resonance. Therefore, this will be the more stable conjugate base. If that's the more stable conjugate base, this acid will be the stronger acid. In the case of this conjugate base, this cannot do resonance. So the negative charge is stuck on the oxygen. And since that conjugate base is less stable, this acid doesn't want to form that less stable conjugate base. Therefore, that acid will be considered the weaker acid. So let's see. So the question asks us, why is acetic acid a stronger acid than ethanol? Acetic acid is a stronger acid than ethanol because its conjugate base is more stable than the conjugate base of ethanol. Therefore, the acetic acid would willingly and readily lose its acidic proton, in order to form the more stable conjugate base. This is the reason why acetic acid is considered a stronger acid than ethanol. This is where we'll stop today. I hope I've been able to help you prepare for your forthcoming exam 1.